Innovation Lab. So this event is hosted by OIL, and OIL is the hub for advancing the open source, open data, open culture, and technology integration within engineering students. And usually we have a weekly meetup on every Friday night, and we will invite speakers to have a talk. And we cover a variety of topics, including big data, security, and web development, and so on and so forth. So if you are interested, you can attach me, and you can we can find some time to have a talk here. Okay. So without further ado, we welcome our speaker today. Today we are very happy to have Yuhan and Li Yuan here to give a talk today. Okay. Welcome.
Good evening, ladies and gentlemen. Welcome. And thanks, OIL, for giving me this opportunity to have this sharing about blood pressure measurement. Well, all of you, I think that you might know about the blood pressure, but in the summers, we have developed a design of some products to detect this kind of blood pressure with more accuracy and in real time continuously. So, let's begin with the significance of blood pressure. So, you see, blood pressure is a very common term in our daily life. But, you see, these kind of cardiovascular diseases, which happens to be the #1 killers globally, or the major death cause in the world, actually have some relationship with the blood pressure. For example, the heart attack, the stroke, and all of this kind of disease can actually detect a normal blood pressure. And so, what is blood pressure? In the Wikipedia, the blood pressure means that the pressure that the blood applied to the external wall of the blood vessel. And this is just the definition, but you have to know the information about the systolic pressure and the diastolic pressure. The systolic pressure is the highest point of the blood pressure waveform. This is kind of a blood pressure waveform. And DP, this diastolic pressure, is the lowest point. So these 2 points determine the health condition of your own blood pressure. Well, you know, a heart is like a person. So what if we give this person low pressure to work? They may act unproductive, right? So it's the same about the heart. So if your heart is in low pressure, which means that they cannot provide enough energy or provide enough material to support your daily life. So you may get dizzy, you may get hungry very easily. But what if we give it too much pressure? Like a person, if you're in a very high pressure, you will feel nervous and you can't stand it anymore. So maybe you explode. And this is same as the blood vessel. The blood vessel in a higher pressure can actually cause death. You may feel nervous, you will not feel comfortable. So indeed, blood pressure measurement is needed. Well, luckily, today we have a lot of blood pressure measurement methods, and all of them can be divided into 2 categories. The first is the direct one, the direct measure, which means that you use a tube, or we call it a catheter, to stuck in your body and to detect the real blood pressure. Well, it's very accurate, and it can detect it continuously, but it's kind of disgusting. Because you imagine that there is a tube, there is a catheter stuck in your body to detect the blood pressure, and you will not feel comfortable, right? You will not feel good. And one more thing is that it's so expensive. The catheter cannot be reused. You can just use one for one time. So once you use the catheter, you have to dump it and replace another. And the catheter is very very expensive and it's complicated to use. So people are very smart. They invent some so-called indirect measure, which is the normal daily life to measure blood pressure measurement methods that we use every day. Like they apply some photonic or the light, and the ultrasonic or the sound, or just the external applied pressure to detect this kind of blood pressure. But it's not yet. It is so easy to use, it's not expensive, and it's non-invasive, so you will not feel comfortable. But it has problems. For example, the low accuracy. Well, because there are a lot of aspects that can affect this kind of measure. For example, the motion artifact, which means that if you move a little bit, your result will not be credible. Or the position of the arm you detect is also affect this kind of result, which means that if you put the cuff in the wrong place of the arms, you will have a not very good result of your blood pressure, and it cannot detect it in the real time. So our purpose, our thinking is, why don't we just combine these two methods together, which means that we can have a real-time and continuously detection of the blood pressure, and also a non-invasive and easy and convenient one. So this is the goal. It's our purpose. We want to establish something that can non-invasively detect the blood pressure in the real time. Well, fortunately, our senior PhD students have established an algorithm that can detect the blood pressure, detect the SBP and DBP, which is called the pulse transition time algorithm. Well, I will not go through this algorithm here because I myself not well known this kind of algorithm. But the point is, there is a relationship between the pulse transition time and the blood pressure. So what is pulse transition time, or we call it PTT? Its definition is the peaks of the electrocardiography, or the ECG, and the tonal arteriography wave, which also means human pulse. So you can see from this graph that the time interval, can I use this? Sorry. The time interval between this point to this point, we call it the PTT. The PTT has the relationship between the blood pressure, and we can come up with a formula to detect or to calculate the SBP and DBP like above. So our products or our design will have three parts, right? The first part, the sensor part, which is the ECG and TEG sensor. The second part is the data acquisition, or we call it the circuit part, to get the information of the sensor that detects it from the human to the circuit. And the third one is data analysis, or we call it the algorithm part. So here myself, I will introduce the sensor part here, and will leave the last two parts to my teammates. Well, ECG sensor, I will not go through it because we just buy the commercial. But the pressure sensor, we made it by our own because we want to have a very small, tiny, and flexible pressure sensors rather than those kind of with a very large curve, and it's not convenient. So how do we make our flexible pressure sensor? Well, actually, there will be three types of the pressure sensor. The first type is piezo-capacitance, the second is a piezo-resistive, and the third is a piezo-electrode. Now here, I'll just go through the feature of piezo-resistive pressure sensor because we just use it in our design. Well, you can see that there will be 4 layers of our pressure sensor. The PS substrate, which make it small and tiny and flexible. The second is the electrode. We use the interdigit design to reduce the contact impedance. And the second is that the most important one, The carbon decorated fabric, or we just call it FC, is the material that can use for this pressure sensor, and the PEM for encapsulation. So what is its principle? What is the working principle? Well, imagine there's a little worms or little channels roughly just put on this electrode, and initially without the pressure, their contact is not that good, right? Not well with the electrode. And the second is it's so rough in its bulk. So imagine if there was an electron trying to go from one side of the electrode to the other side, it has to go through a very long distance, turn around in a very circular paths. So which means that the resistance of this pressure sensor without press is very large. But what happens if we apply some pressure in it? So under the pressure, two things happen. First, you can have a better contact, right? A better contact between the material and the electrode. So the contact impedance reduced. Second, this channel for the electrons will be more tighter and straight. So the electron will be easier to go through this kind of the channels from the one side of the electrode to the other side, which means that the bulk resistance also reduced. All in all, the resistance of the pressure sensor reduced. So you can just see it as a variable resistance. Well, we do have a lot of data, blah blah blah, and what's important is that we found that a concentration with 4% of carbon into this FC will have a the sensitivity to detect the human pulse. So you can see the graph C, yeah, and here we show the FC4's contact impedance and bulk impedance when applied an increasing external pressure. So before the saturation point, they decrease linearly, well, approximately linearly, from the range of 0 kilopascal to the 5 kilopascal, this range. And one thing to be mentioned is that the contact impedance is much greater than the bulk resistance. So which means that it's actually the contact impedance dominate this kind of reduction of the resistance. So we have made our own resistance pressure sensor, and you can see that it's flexible, so you can just put it on the wrist and just detect the human pulse. And this is the result. Well, we also compare it with the normal method to detect the human pulse, which is the PPG. This kind of PPG methods use the photonic or the light to detect human pulse. Well, if you zoom in these two kind of methods, here the graph B, we can see that the shape of the FPS, the flexible pressure sensor, is similar to the PPG wave. And we use this kind of the wave to calculate the pulse transmission time or the PTT, and we calculated as SPP and DVP using the algorithm, and we found that yes, they are similar. So we can use this kind of pressure sensor and PTT algorithm to establish our own design of the blood pressure measurement. And the next part is, well, I will let my teammates, a very young and beautiful lady, Liu Han, to introduce the remaining part. Thank you.
And now I will introduce the data acquisition part first. Here is our multi-modality sensing circuit. And based on our PTT algorithm, first we need to detect the peaks of the ECG and TAG waves. So we have the ECG and TAG acquisition part, of course. And then we have a power supply part to provide several constant voltage for the whole system. And the MCU part will help to calculate the path transmit time from of these two ECG and TAG waves. Now let's see the TAG acquisition part first. As my groupmate introduced, our TAG sensor is just like a variable resistance. So we had the IEF 2000 chip to provide a constant current 100 microamp to the sensor. Then we can measure the voltage change of the sensor, which will reflect that the different pressure that the sensor senses. And because the TAG signal is usually no more than 80 millivolts, and it's very too weak for us to detect it directly. So we use the LS351 as a single anti-forward amplifier. Its gain is determined by the R1 and R2 and is about 60. And because it's the negative effect of the noise, so in order to improve our accuracy of the result, we add a simple high-pass filter circuit. Its frequency is about 0.3 Hz. And the last part is the signal converter part. And I will talk a little more about our PTT algorithm now. And because our algorithm is detect the pulse transmit time between two peaks, so it's not that necessary for us to know the magnitude of the peak. What we need is that when the peak appears. And what's more, our MCU has a function that it can calculate the transmit time between two pulses. So in order to calculate the PTT time in a convenience way, we had an idea. We would like that the peaks of the waves to be transformed to the pulse, and then we will do a digital analog to digital conversion to make the detected signal waves to be a digital one. We choose the voltage comparator to achieve this goal. In electronics, the voltage comparator means that we will input two analog voltage, and then it will output one digital output to indicate that which value is larger. So we send the output of our high-pass filter as the positive input of the comparator, and then this variable resistance is connected to the positive and negative 5 volts. So when we change the value of the resistance, we can have a different value of voltage to be a threshold value for the comparator. Then, if our signal value is lower than our threshold value, it will output high, and otherwise it will output low. So this comparator can also achieve noise immunity. If our value is lower than the threshold value, it will all output high. And maybe you will say that in such a method is not very convenient because we have to change the variable resistance in a manual working each time. So we will improve this part of our circuit later. We would like to add a feedback part to the input so it can achieve the aim of change the threshold value automatically. And the next part is the ECG acquisition part. The ECG is the process of recording the electrical activity of our hearts over a period of time using the electrons on our skin. In our project, we use 3 electrons, one on our left arm and one on the right arm as the positive and negative electron. And another one is also placed on the right arm as a reference. ECG signal is typically about 19 millivolts with 1 kilohertz, so it's hard to detect it directly also. The AD620 is used as an amplifier here, and its gain is determined by the RG. The gain is about 500, and then to avoid the negative effect caused by the noises, we add a bandpass filter here also. Its frequency is from 0.3 Hz to 15 Hz. The C part is a driver part because the distance for the electron to transmit from the heart to the waist where we monitor is too long, so we had a driver part for our circuit. The R5 and 6 provide the average of the voltage of the positive and negative electron, and it's the inverting input part of the driver also. And then this path gain is determined by R7 and 8 is about 100. The C6 here is help to prevent the oscillation and help to maintain the stability of our circuit. The final part is just as the TAG acquisition is a voltage comparator, and a little different is that the output of our ECG signal is to be the inverting input of the comparator. So if our ECG value is lower than our threshold value, it will output low. And next, we can see here is our power supply. We use 3 AMS1117 chip as the voltage regulator. And we connect the output pin of the ground pin of the first 5-volt chip to the output pin of the second 5-volt chip. So then the ground pin of the second 5-volt chip can provide us the negative 5-volt power supply. And the capacitors here are very important. They help to avoid the negative effect of the variation in noises from the voltage outputs. And now we can see here is the result of and so sorry that there may be some technical problem from our PPT, and I will show this result later. Here the picture will talk about the analog signal wave of the ECG and TAG wave we get, and the digital wave after our signal converter. And after getting the PPT time of the circuit, we will come to the MCU part. The reset circuit and the crystal oscillation circuit is two basic parts to make the MCU working. And then our Bluetooth will help the circuit to send the PTT data to our APP on the mobile phone. Here is the data analysis flow figure. After the APP receives the PTT data from the Bluetooth, it will upload this data to the server cloud, to the cloud server through the internet. And the cloud server will have the storage and calculation function and get our final result, the blood pressure. And then the cloud server will send back this result to our internet and the APP. Our APP also have a function that it will plot the blood pressure in graphs. And here you can see is our APP. And here is our cloud server. We can storage the real-time data. This is our final system. We use the flexible TAG sensor, flexible ECG sensor. The TAG sensor is put on our pulse, and the TAG sensor is put one on left hand, two on the right, one on left arm, two on the right arm, and then our circuit will detect the ECG waves and the TAG waves from the senses, and then send to the APP through our Bluetooth. The mobile phone will have a conversation with the in-cloud server and then get the result of the blood pressure. Here is a video.
This is how all of our system works and results. And thank you for your attention. So if you have any questions, yeah, don't hesitate to ask. Actually, yes. We are just considering to minimize this kind of size of PCB, or we just don't use PCB or something more advanced like an integrated circuit, but it's too expensive now. So with the limited resources, we just use this PCB. And any other questions?
Why do you want to upload the data to the cloud? Why don't you do the calculation locally?
Yeah, that's a good question. Actually, we consider this kind of the method to use the mobile phone to calculate this kind of PPT algorithm. But the thing is, first, the cloud server has a storage function that can store a lot of data because you are continuously or in real time detecting this kind of blood pressure. So it's a very large data and to be generated. So it's more convenient to upload to the cloud server. The second is that the burden of the mobile phone has already quite large because you have to open the Bluetooth and open the internet to conversation. So this kind of the algorithm in the cloud server is reduce this kind of burden. The third is with this kind of cloud server, your physicians or your doctors can access this kind of data, the history of data of the patient and blood pressure very easily. And the fourth reason is that if we have a better algorithm for PTT, better than PPT, we can update it in the cloud server much easier than in the mobile phone. Hope I can answer your questions. And any other questions?
I want to know, so it's necessary to use two kind of signals to get blood pressure, or that's because you get more accurately, or it is without those two types of signals you cannot get the blood pressure?
Actually, it's kind of based on the PTT algorithm, and PTT algorithm require these two kinds of signals, the ECG and the human pulse. So yes, we do require these two kind of signals.
Could see why this kind of thing is.
Oh, sorry?
Could you explain why, how is two kinds of things?
So that is the problem algorithm, which I happens to not know this. Yeah, and maybe there are some papers we can refer to.
Is it?
So you have two kinds of signals. One is electrical signal, one is mechanical signal. So when you have a pulse, you will have generally two kinds of signal.
Yes.
Electrical signal goes faster, so then you will come to your sensor. And then you have a mechanical goes slowly. Then you have a delay. And then this delay is related to your body information. That is how big is your vessel and how high is your blood pressure. So this has a relationship. And then if you detect the pulse heat difference. You will get you know the water pressure.
Yeah. Thank you for this answer.
So is it normal or is it not?
It has been researched for many years.
Yeah. So, any other questions?
So it seems that the algorithm does not require all the historical data,
Just the time. The time interval. Yes. Yes. Any questions? So if not, and this is the end of our presentation. And thank you for coming. Thank you.
Thank you very much for the talk. And we can have a brief discussion in the next room, and we'll provide some soft drink and snack as well. So we can move to the next room and have a brief discussion if you want. Okay. Thanks for coming today.